Hi, good afternoon. Welcome to the last session that's between you and the drinks today. My name is Mohan Kumar. I'm a fellow at Intel. I've been in the data center group for a very long time. I worked in Intel all my life. It's the only company I know. I've been there for 23 years at this point. Somebody gasped when I said that. I'm not from the California area, so I'm not. There's only limited companies in where I live. So first of all, I want to tell you about what I'm going to talk, what my topic is about. So the topic I gave to my folks was, they asked me to talk about rack scale and OCP hardware. So being an engineer, I don't know how to come up with fancy names. I said, okay, rack scale and OCP, that's the title of my talk. And it went through, and that's the name that it. So, and that's the transformation they made. So thank you, marketing. I owe you one. So my goal was to give you an overview of the rack scale and kind of show you how it aligns with the OCP hardware, and to show that they're complementary in every way possible. So, first of all, before we go there, we need to talk about, why do rack scale at all, right? I don't like the bill. Let's just finish the bill. So, if you look at a data center of today, whether it's an IT-based enterprise data center, there's lots of inefficiencies because, there's standard resources. You put in your PCI card in a certain place, or your SSD in a certain place, it's not universally utilizable, so you have a lot of underutilized resources sitting in your data center. And at the same time, so the other problem you have is that the data keeps growing at a very rapid rate, which means the practices that in the enterprise IT which we used to have before, which was, we'll roll in another thing, we'll test it, we'll validate it, we'll bring it online, and then if you have to add more capacity, we'll go do the same. That model doesn't work. So the hyperscale folks have got this right? They already had this problem in the Facebooks of the world already, and they already figured out the solution for how to scale, where you can just bring in more resources and everything just scales along with you. And we really need that if you're going to keep pace with the data growth, even in the enterprise world. And the agility is the rate at which you are able to deploy a service in your IT environment, right? And this is really, and it used to be like 10 years back, given I told you I've been doing this for 23 years. 10 years back, it was a matter of months after I submitted a form. It was actually typed in with my name and the request, and a server showed up that I can do whatever I needed to do. Even a few years back, when I wanted to get like a storage, a portal to share information, a data portal to share information, it's SharePoint or GitHub, whatever, I would send a request to my department admin. Discussions happen in some smoke-filled room, and weeks later, I would get my URL that I can go store stuff. Today, I don't know about other places, at least at Intel, it's a click, and everything gets done. And that's wonderful that at least for this simple stuff in an enterprise environment, things are getting easier. What really needs to happen is not just services and servers, and whatever resources that you want to have need to have that same agility, where you want to be able to click and say, I want a server of this kind. I mean, we do this all the time at Intel, where at least in the data center team, where you want to go take a server and set some things. I want this bias settings to be different, and let's see how this workload performs under the circumstances. But today, every time it's a do-it-yourself project, because I take the system, I boot up the BIOS, I hit the OS. It'll be wonderful to have to reach so the best way to fill the gap is to create it yourself. So hopefully one day we will have this rack scale solution essentially addressing that problem, where you can click a button and get a server, and then you can go configure it the way you want and get going from there. So first, before we even talk about how this works with OCP hardware, we need to talk about what rack scale architecture is in the first place. So essentially, it's a logical architecture. So we're not really prescribing you must build this platform with this components type of thing. It's a logical architecture, and the goal of this architecture is to essentially allow there are three things that we're trying to do, right? One is to not just focus on, if you look at like management of the platform, it's essentially divided into compute management, storage management, and network management. And that kind of goes back to the days when they all used to be supplied by 3 different vendors put together and magically made to work by the power of the IT people that somehow knew how to bridge these things together. So we wanted to have a single plane of gas that allows you to manage all these resources in a uniform manner. The second thing is to avoid the stranding of the resources, the ability to think of resources as resources and then be able to put them together and pull them and compose them together. So that kind of avoids the stranded resources because, and I'll show you later, right? For example, in SSD, why is it stuck in, if it's a high performance SSD especially, why is it stuck inside a server? Why is it not something that you can deploy to any server as you need, right? And doing all these things, and last but not least is to create a solution that is able to interoperate, right? It's one thing, there is lots of converged infrastructure solutions, but the idea is to create a solution, an architecture that allows you to say, under this umbrella, there is a number of vendors can create solutions and they interoperate with each other. That's essentially the direction of the rack scale architecture. So the architectural framework for this is, given that it's a pool system, in order to allow this scaling, the hyperscale type scaling, we have the concept of pod-wide management, which basically means pod is essentially to us like tens of racks. So across those tens of racks, you can add racks, and the management infrastructure is essentially able to understand and comprehend that without any seamlessly, essentially, right? And the architecture is built essentially using, and it understands the network fabric, whether it's Ethernet. I mean, most of the cloud is Ethernet anyway, right? So to essentially solve the problem of, in this rack, I want the network to be configured this way, and the other rack, I want it to be configured this way. I want them to be connected. All those things are comprehended, and then to be able to have the same seamless view for both compute, network, and storage, right? So that's kind of the broad framework for what rack scale is. And then let's click into each one of these in the next looks like 17 minutes and talk about where we are. So the first one, the one that we are at a point where we are able to solve the problem is in terms of first thing you have to solve is the management framework, right? You have to take all the resources that exist in a rack, right? Whether they are compute, network, storage, environmental, all of them together and have this API. In our case, we call it the manageability API. And this API is the foundation for everything we do. It discovers, it can provision, it can compose. All of that happens. All of the awareness of what's underneath you is provided by this API. And this then feeds into our pod manager layer, which runs across multiple. It can run across multiple racks. You can put it on one rack if you wanted to, but. And this layer is where you see the resources, and every time, so at this layer you essentially see a single point, right? You go to the single point, and all of the resources show up under that single point. It's not a pass-through interface. It doesn't say, oh, I happen to know so many things, and here is an IP address to go talk to that guy and find out. It essentially is the aggregator, and it's also the composer. So this is the entity you go to and say, I would like to have a compute node with these things, attributes, and put it together for me, right? One of the things, and I'll talk to you later about the orchestration layer. So we want to also, again, basically supply the common API to orchestration layer, whether it's Microsoft, VMware, OpenStack, or somebody's doing a custom solution. Especially on the OpenStack part, one of the things that we see is that everybody is focused on the overcloud management, meaning once you have got this OpenStack up and running on those platforms, and you're scheduling VMs. They are in their zone, if you will, right? The undercloud, which is, how did you get that up in the first place? How did you solve the provisioning problem? How do you reprovision? Those are still in infancy, if you will, right? And this is our goal, to solve that problem through the rack scale architecture. So now, since I said we want to talk about alignment with OCP as well, so I'm kind of showing you some of the concepts of the platforms we have put together, and they should, those of you that have seen the other platform, they should look awfully familiar to you. So the compute node, so essentially, just to give you a quick overview, the front, it's a slided architecture. So if you look at the sleds, it could be a Xeon sled or a microserver based sled, or a SOC sled, I should say. And the back of it, essentially, the back plane of it essentially is the one that adds the RSA nest to it. If you look at the front of the set, this looks very much like the OCP Leopard. In fact, it's that design that we have taken and essentially added the back plane and the management framework, management connectivity to create this, create the rack scale architecture. And the storage node solution that you see on the other side, on the right-hand side, is again should look very familiar. I mean, my graphical skills stop short, but it should look like a Knox to you. So so from the point of view of a compute and a storage node, it's very much built on top of these things. But the management framework is what we added. And since we are a logical, so there are three pillars to our solution. One is it's a logical architecture, right? The other is that we're a reference architecture. So we like the things that we add, like the management backplane, we have contributed into to make it available openly so everybody can adopt it. And then also like the firmware and the software that goes along. Like I talked about Pod Manager, which is a piece of software, and I'll talk to you about management engine, which is a piece of firmware. All of this we have also been releasing into as reference into open I don't know if you call it open source, but been openly available to everyone, freely available to everyone, I should say. So I've talked a lot about composition, and one of the places this shows up, I deliberately chose somewhat of an abstract graphic here. This should look very much like, if you think about it, this is a different way of looking at, if you will, lightning. So in the rack scale terminology, we call this the pooled NVMe controller. Again, engineers, we come up with names. This hasn't gone through the marketing change to something really cool yet. So essentially, instead of having your, very high performance SSDs attached to you locally, what this allows is to have the drive speed disaggregated and then on demand. I'm showing drives because it's easier to comprehend them, but it could be FPGAs if you wanted to, and other devices. And the idea is that then you can essentially compose them into any device, any node that you want, whether it could be a server node or a storage node, right? So if I fold this into a single server and assign all the drives to that single server, you have Lightning basically. So the difference there is that we are essentially using that same switch as a multi-root switch. So we have multiple host domains that are feeding into it, and we also have a management link because we want to have a common API layer. And PSME stands for Pool System Management Engine, and what it does is to give you that common infrastructure that allows you to have the same view and also to go compose. You can, so the PSME will say, I found this pool system with these number of drives and these number of host cables, and then you can say, and the pod manager who has got higher level of awareness can say, take server 1 and assign drive 1 to him, and the zone will get created and connected. It's software, it's just configuration and materialized as a drive under that. So there's a lot of goodness to doing this in general. One is, you avoid the single point of failure with the server node or the storage node, whatever it is. And also, we also allow full and partial drives. So potentially what happens is that you have these high performance drives will have lots of IOPS available to you. And you want to be able to use those, so in the interest of not leaving standard resources, you may want to use up those resources in a meaningful way and assign it as, if you're not using the full capacity, full capability of the drive, then you are able to use it up by assigning it to multiple entities, right? So, and it also helps, of course, with the workload migration in this kind of a hyperscale environment, because you don't have to be stuck with where can I find another place that has this capability. The capability will come to you if you want it to. And in some sense, we understand that we are kind of blazing the trail, because like software, if you look at if you look at the Ceph type software, they're not there where they can dynamically take a drive and use it as a journaling. But what it does allows you to do is to have this warm tier, cold tier application. You could take a storage node, and if you wanted to compose a system with a bunch of storage nodes and assign these drives as your journal for Ceph, you could do that. Or they have, I think, a new thing called Firefly, which allows you to have the caching layer as a hard tier in at the compute node level itself, and you could do that also with the high performance 3D crossband drive, for example. So there's lots of flexibility that this kind of an architecture brings in my mind. And you can see from all the what we showed, it's very aligned with the OCP hardware, right? It's all we're adding is the management backplane. So now we should talk about what that management backplane is, right? So essentially, we are managing this at a multi-node level. Again, that's a very OCP aligned concept. So these multiple nodes, which is number of sleds in your rod, we call it a drawer. And each of those multi-node is managed by a pool system management engine. And the pool system management engine exists to provide this common API view through which we can essentially go figure out what resources are there in the system, and and where they are, right? And where they are comes from the fact that we have a management switch that essentially allows you to say that not only we want to detect the resources. Today, one of the problems is that at a high level, when you go to the orchestration layer, the details get abstracted away. So what we want to do is to have this ability to say, I want to find a Xeon with AES-NI and send my workload there. I want to find a drive that has got X capacity and this amount of bandwidth and this number of IOPS and send my workload there. Those capabilities, we expose through this API. So, and the other thing is that there is a natural, in hyperscale architecture, there is a natural fault domain problem that comes along with it, right? Probably your rack is plugged into a single power supply, right? Single power source, I should say. And you don't want the failure domain to be so high. So whatever the failure domain information is, one of the reasons we are location aware is we're not talking about GPS location. What we're talking about is essentially exposing that all these resources are part of the same failure domain. So if you're going to make a erasure coding of your data, do not put your data in two storage nodes that are on the same failure domain. So it allows the orchestration layer to be aware of it and do that. And there's another piece in green that you see that's called rack management module, and that's there to do the environmental management, like cooling and power supply management, so power and thermals and whatever else that goes along in terms of sensors in the platform. And again, you don't have to implement, in the way we implemented our reference platform, these are all, each one of them is a discrete component that exists by itself. But there is no need for it to be that way, right? If somebody did a rack that's where the logical architecture comes in. Somebody could say, nope, I'm not going to do that. I'm going to have my power and thermal be not disaggregated, but controlled in units of 5U, whatever the number is, right? And that's fine, because then the RMM functionality needs folded in, and we expect the RMM API to get surfaced through the corresponding PSME at that point. As long as that happens, it's still, in our mind, a rack scale architecture. So we're not saying you must go put this piece of silicon in there and run this piece of firmware in there. What we're looking for is the functionality. So, so since we're talking about APIs, what is this API, right? So at the pool system management level, essentially what we did was we looked into the DevOps world because that's kind of the hyperscale world is servicing, and they're all they're all essentially REST and JSON based. So when we said, okay, let's start going out and designing a REST and JSON based solution. And in the meantime, the DMTF folks were building Redfish. So we took Redfish as the base and then extended on top of it because we didn't want to fragment any existing standard. So we just built it on top on wherever the multi-node. They are primarily focused on a single node today. So we wanted to add the multi-node capabilities, storage, and networking, and of course PCIe for the pooled NVMe controller solution I showed you, and essentially build that into a common API. And then we also added all our telemetry value because we wanted to say, hey, there is a performance problem here, or this node has failed, or this drive has failed. All that information has to be exposed up to the orchestration layer so they can make meaningful actions on the basis of that. And the only thing that the pod manager layer adds on top of doing this type of asset discovery is the ability to do the composition. That's where you go in and say, you can say this is my requirement and go compose a system that meets my requirements and come back. Right. So from a hierarchical standpoint, so if the pod manager essentially sees if it views its view of the rack is essentially the management elements inside the rack, because those are the elements that tell the pod manager what exists in the system. And so it goes and queries the rack management modules and all the pool system engines, and they give them the asset information, the location information. And one of the key things for us is to be not do any of these things in-band. And I'm going to the definition of in-band to me is that I don't want to run run an OS there, because then immediately you're violating the control plane data plane separation. So the idea is to, without deploying an OS on top of it, get all the information about what CPU, what are the attributes of the CPU, how much memory do you have, what type of memory. I mean, these days you can have more than one type of memory and capacity, what type of drives, what capacity, what IOP. Are they capable of all that information gets exposed, bottom up to the pod manager. And pod manager itself, in all of this, to keep it simple, I didn't show any of the high availability architecture in terms of taking the pod manager and building a hierarchy, or building high availability by stretching this into multiple domains, because you don't want to have a single point of failure at your management infrastructure level. You want to have that solved also. We do solve that, but just to sake of brevity, I didn't put those in the pictures. So if we take, for this purpose, I'll just take the OpenStack. So in terms of all the resources that we found at the pod manager level, then we need to surface them up to the appropriate controllers. So the information that we expose, as opposed to what would have normally shown up there, is to essentially show the fact that not only the resources, but also these resources exist in these domains. So for example, if you take the OpenStack, the compute goes to Nova, the networking resources go to OpenDaylight, and the SDS, the storage resources go to, for example, Cinder, let's say, right? In order to make the availability zones work, we also expose hey, these resources are together in the same failure domain information as aggregates. This aggregate consists of everything that's in this pod, everything in this rack, everything inside this subunit of the rack. And that way, if you wanted to, either for fault domain isolation, or for, if you wanted to do clustering, you want to have proximity for the resources, that awareness is being exposed as part of this API up into the orchestration layers. But definitely where it helps is when you're trying to build your storage solution, when you do the pod-wide storage, you can say, these things in one availability zone, and these things in another availability zone, put them together to make a solution that is truly going to be has higher availability compared to just having them deployed and hope they work, right? And the other goal is that like I talked about, the undercloud provisioning is a problem that needs to be solved, because once you get there, there seems to be an answer. What we need to do is to make sure that you can get there in the first place, and you can change. It's not data centers are not static; they're a living, dynamic entity, right? So if you wanted to reprovision the data center, at the undercloud level, you want to be able to go say, here are all the resources I found. Here is the compute node. Here is the storage node. Here is the networking elements. Now put it together, as opposed to saying, here is a bunch of resources I found. You tell me what you're supposed to do, which is what most solutions do today, right? And that's the goal, to get there, to be able to show that with this architecture. Okay, looks like I'm running out of time, so I'll quickly summarize. So our goal is with Rackscale architecture is to deliver the next generation data center architecture, and working along with OCP hardware to take it to a place where we have a common framework for hyperscale deployment, and we believe the open OCP hardware, as we have shown through our own reference platforms, can be taken and basically be managed through the Rackscale management API. And the resources I forgot to put the hardware part, the management hardware part, and the firmware, software, all of them are available on the link that's posted there. I think I'm just about out of time. Thank you so much. Thanks for listening.